Okay, let's go. So where did we leave off? So last time we solved the Basel problem. Sum 1 over n squared, which is zeta of 2, being pi squared over 6, modulo, I mean, we solved it how Euler solved it, but modulo the rigor, the last thing that I needed to prove for you was that pi cotan of pi z is equal to a sum 1 over z plus n over all integers. Is that right? This was now yesterday, so I think even now, even I can remember what we did yesterday. Okay, so
Professor,
yes, Ishan.
you were mentioning that you're going to talk about the convergence of the guy on the right.
So we did talk about that yesterday. The way that we
I remember now.
interpreted this
Okay.
was to say it's 1 over z plus a sum over all the positive integers. And if you group these, you get something like 2z over z squared minus n squared, if I recall. So the point
I
is
remember.
this converges. This is like 1 over n squared, which is summable, whereas this 1 over n is not summable. So the way in which I mean this function is, I really mean this function, but it's easier to see some of its properties somehow if you write it like this. Does that make sense? Any questions so far? Okay, so this is the last thing that I have to justify for you. All right, so first of all, I want to do this. This is kind of fun because this is a baby modular form. So let me argue a couple of things. Let's call this function. So this is my claim. This is sort of the definition of this is by which I mean this. And so let me call this function f of z. Okay, and the one thing I want to point out, there's a couple of properties of f of z. First of all, it's invariant under z goes to z plus 1. That's simply because cotan is cosine over sine, and sine and cosine are invariant under shifts by 2 pi, but the ratio is invariant under shift by pi. Right? The tangent function and the cotangent, you know this, the cotangent function. What's the cotangent? Tangent is like this, and it's invariant under pi. This is from minus pi over 2 to pi over 2, and it has the same value as you shift over. Anyway, right? You guys are happy with this? Yeah. So it is invariant like this. And because this is cosine of pi z over sine pi z, I guess with a factor of pi up front, near 0, cosine looks like 1 and sine looks like z. So this is the second thing my second remark is that near 0, f of z is equal to 1 over z plus a function that is holomorphic near z equals 0. Okay, so it has a simple pole, and that simple pole has residue 1. Okay, that's just from the expansion of sine. I'm using that sine of pi z starts out as pi z plus lower order stuff, whereas cosine of pi z starts out as 1 plus lower order stuff near 0. So the ratio with an extra factor of pi starts out as 1 over z. Okay, so if you're happy with that, then let me set the function delta of z to be, do I want to call the right-hand side something? Well, let me just set delta to be pi cotan pi z minus this sum 1 over z plus n, by which I of course mean this. Okay, this function delta is just like both of these functions. You see, with this function, is it obvious that it's invariant under z goes to z plus 1? Not really. You have to do some computation. But if you look at it from where it came from, this is obvious it's invariant under z goes to z plus 1 because it's just changing which integers you're running over. Does that make sense? So both of these functions are indeed invariant under z goes to z plus 1, and so is their difference. And look at what we've done. This is nice and regular near 0. So this starts out as 1 over z plus something holomorphic. This is holomorphic. It's not holomorphic at the, it has poles. It is holomorphic near 0. So both of these start out as 1 over z. And so when we take their difference, this delta is holomorphic at 0. We've subtracted off the 2 polar parts. Does that make sense? The 2 principal parts. But it's invariant under z goes to z plus 1. So it's also holomorphic at all the integers. And at all the integers. And so it's just an entire function. Okay, so all of the poles, both of them have poles at the integers. And just from the invariance and looking at 0, we can see that the residues at those poles exactly cancel. You believe that? Great. Well, so if we could show that this delta is bounded, then it would be a constant, and then that constant would be 0. How could we see that the constant is 0? There's sort of a really easy way. Is this function even or odd? Cotan. It's cosine over sine.
Odd.
Odd, right? And this function? Maybe it's not immediately obvious, but it should be obvious from here, because if I replace z by negative z, this gets a negative and that gets a negative, that doesn't change. So both of them are odd, so their difference is odd. An odd constant function is 0. If you're invariant under 180-degree rotation and you're constant, the only constant that's invariant under odd functions are 0 at the origin anyway. So if you're constant, then you're 0 everywhere. Okay, so all we have to do is prove boundedness. So let's look in the complex plane. We already know that we have this invariance under z goes to z plus 1. So it's enough to prove boundedness in the strip minus a half, right? Because delta is going to look the same on all of these vertical strips. So in here, need bounded in this range. So far, so good. Great. In any compact region, let's say out to -1 mun, it's holomorphic. So it's obviously bounded in here. It's bounded since holomorphic in this range. And this is exactly where we've removed the pole that each of these had at 0 by exactly canceling out the principal part. So we're worried about what happens up here. So here it's bounded, check. So we need it to be bounded in the region, let's say y is bigger than 1, and by symmetry y is less than 1. Okay, we need to prove that this function is bounded. If it's bounded, then it's entire and bounded, so constant, and odd, so 0. Okay, in fact, each of these pieces separately is bounded, I claim. So my claim is that both f of z and this sum are both bounded. This doesn't have to do with their difference. They're just individually bounded. Bounded for x between minus a half and y away from 0. So these individually have poles at 0 and at all the integers, but away from that pole, which we've subtracted off, they are indeed bounded. That's what I claim. Let's see if we can prove it. Does that make sense? So far, so good? Let's see if we can prove it. Okay, so again, f of z, this is pi cotan of pi z, which I'm getting a little ahead of myself trying to write this as something over something. Cosine is e to the I whatever plus e to the minus I whatever over 2. I'll keep the 2 for a second. Sine is e to the I whatever minus e to the I minus whatever over 2I. So I think all I have to do is put an I there. Now I'm going to do something slightly funny, maybe, which is just to multiply. All we have to do is simplify this slightly and use the fact that x is not doing anything and y is at least 1, and we should be in good shape. I think if I multiply this by e to the I pi z bar, will that work? Let's try. Let's try multiplying the top and bottom by e to the I pi z bar. I hope this will work. So we have pi I. E to the I pi z bar times this gives me an e to the z plus z bar. So I get 2 I pi x plus, here I have z minus z bar, or rather e to the minus I pi times z minus z bar. And z minus z bar is 2 IY. I guess I want to do this because of what I want is for, so all that does is makes this, okay, sorry. Let's try it again. Let's try it again. We were very close. I think I want the minus sign. I'll show you why in a second. So what do I get here? I get an e to the I pi z minus z bar, which is 2 IY. Good, now I'm happy. And here I get e to the, minus I pi z plus z bar. Whoops, I dropped an I. Z plus z bar is 2x. Everybody happy with the numerator? Okay, denominator is exactly the same except with a minus sign. E to the, so let's simplify it already. So it's going to be this same thing, which is e to the minus 2 pi y, and then a minus sign, and then the same thing here, which is a minus 2 pi I x. Great. Okay, now we're done, because once we put absolute values on everything, the numerator, you see this thing, this is e to the minus 2 pi y, but y is at least 1. And so this is some very small number. And this is a number of absolute value 1. So this is, there's this constant pi in front. So this has absolute value 1, and then, I don't know, minus e to the minus 2 pi y. And the biggest the denominator can get is a 1 plus e to the minus 2 pi y. But y is at least 1, so this is like at most, I don't know, 10. It's just bounded, just flat out bounded. And 10 is way overkill, it's much smaller than that. Does that make sense? So it doesn't matter what x is, x can spin all at once, but the y direction, as soon as you get away from minus 1, 1, this thing is just, it just has constant size basically.
I guess addition in the numerator and subtraction in the denominator might be better.
Addition in the numerator.
Like for the bound.
Thank you. That would be better, wouldn't it? Yes, addition in numerator and subtraction in the denominator. Everything else is as is. Thanks, Theorem. That is how inequalities work, isn't it? You put the largest thing on top and the smallest thing on bottom. Okay. Any questions on that? Let's check the bound for the other thing. The other thing, I don't want to use this version, I want to use this version. So the other thing is 1 over z. Now check if the other side, other part, is bounded. So I have 1 over z plus a sum over the positive integers. Z, what is it? 2z? No, it's not z squared. It's 2z over z squared minus n squared. Something like this, right? Okay. Now I put absolute values. Okay. Remember, y is bigger than 1, and x is between minus a half and a half. We're looking in this part. And by symmetry, the same thing's going on down here. 1 over z, beautiful. We're at least 1, so this is a constant. I don't care about the 1 over z, so the 1 over z is bounded by a constant. Here, I'm bounded by, let's see, this is where it will be good to see something. So 2, I'm just going to put absolute value of z. And now what can I say about the denominator? Z squared. Remember, if we look again in this picture, I guess I have to zoom out a little. Z is somewhere up here. I don't know where. This is z. Where is z squared? What's the argument of z squared? If z roughly has argument I, z squared, z is at 90 degrees, z squared is at 180 degrees. So z squared, this is where we're going to use that we've contained x. Z squared is somewhere over here. And where is n squared? N squared is somewhere over here. And so the distance between the two is at least some constant times the actual distance between them. In other words, z squared plus n squared. Does everybody buy that? The argument of z is straight up, and so its square is roughly in the direction of 180 degrees. And so the distance between them is can't get small. In fact, it's of the order, the actual norm squared of z plus the norm squared of n squared. Does everybody see that? Now, this is still not so good, because if I do some naive things, you see I have a sum in n. If I do some naive things, it's not clear that this is bounded in z. So here's what we're going to do. We're going to control this by the integral, let's say from 0 to infinity. Let's call absolute value of z r. So this is r over r squared plus x squared dx. So I'm replacing n by x, and I'm replacing z by r. So that's nothing. I'm just writing the summation as an integral. No objections. Now comes a little bit of magic. This thing is bounded independent of r. So claim, this is just easy calculus, integral of this thing is bounded independent of r. And this is very easy to prove. You make a change of variables, replace x by rx, then what you get is at 0 we still get 0, at infinity we still get infinity. Dx is r dx. I still have this constant r over r squared, plus x has turned into rx, and this is now r squared x squared. And the r's cancel on top and bottom. I have an r squared on top and an r squared that pulls out on bottom. So this is just that constant. And now we're done. So this function is bounded. So this function is bounded on and this function is bounded, which implies this difference, delta is bounded, hence constant, hence 0. Okay? Any questions? All right. So let's talk about zeros. I'm going to come back to Jensen. There's an important formula that I want us to know. Maybe I'll save this for the end if we have time, but it is an important formula. But let's answer the Weierstrass question. So far we're good. So we use this, knowing where the zeros of sign were, we managed to construct. So just let's recap. The key ingredient was knowing where the zeros of sign of z were. We gave a formula, namely that sign of z was the product over 1 minus z over pi n over all n, well, including 0, but 0 doesn't work that way. 0, you have to put a z there. 0 is the only, a 0 at 0, these are the non-zero zeros. You have to separate when zeros are 0 or at the origin, or a 0 that's not at the origin, right? If you have a 0 at the origin, that just means there's a factor of z. So anyway, this formula, knowing where the zeros of sign were, we were able to construct a formula like this, and then what we just finished is a rigorous justification of this formula. So Weierstrass worked out a general theory of such things. So here's a beautiful theorem of Weierstrass. Maybe I should write Weierstrass, but okay, Weierstrass. So this is Weierstrass's theorem. Let f be entire. So I have a holomorphic function from C to C. And say it has zeros at an. All I know about those zeros a priori is that they don't have an accumulation point. Okay, entire and not entirely, let f not be the constant function 0. So ANs have no accumulation point. Equivalently, the ANs go to infinity. Okay, maybe if you like, the absolute values of the ANs go to infinity. There can't be finitely many in any compact region. There can't be infinitely many in any compact region. There can only be finitely many in any compact region, right? That's not Weierstrass. We already know that. The theorem is conversely, is the converse. Conversely, this is the beautiful thing. Given any sequence an with an going to infinity, there exists some entire function having exactly those zeros and no others, having exactly these zeros and no others. So this is an if and only if. If you know the zeros, you know the function. Almost. So, moreover, any other such is of the form f e to the g, where g is entire. And these, by the way, these ANs can be with multiplicity. So there's no reason A2 can't equal A3. So this is with multiplicity. The sequence can have some constant components with multiplicity. Okay, so if you know the zeros, you know the function up to a factor of e to the g, which of course has no zeros. Okay. This moreover is very, so let's prove, let's see. There's two things that I want to prove. Given any sequence, there are no others, And if you allow me 1, then let's prove 2. So the proof of 2 is very simple. If f1 and f2 have same zeros and multiplicities, including multiplicities, then f1 over f2 is regular, remains bounded, is bounded at each of the zeros, is bounded and hence removable at each 0, and hence it's entire and non-zero, entire and everywhere non-zero. And the complex plane is simply connected. We have a function that's non-zero, therefore there exists a log. So there exists a function log of f1 over f2, which we should call the function g. So e to the g is equal to f1 over f2. So f1 is equal to f2 times e to the g, which is exactly what we wanted to prove. So that part's easy. That part I think is not surprising. If two functions have exactly the same zeros with the same multiplicities, you just take the ratio that you've killed off all the zeros. Now you have an entire function that's nowhere vanishing, so it has a log. Sorry, I guess I write a lot faster than some of you. Let me slow down. Okay. I also write sloppier, so there's a trade-off, right? You're probably writing very nicely. Okay, so we have to prove 2. How do we do this? So to prove one, the obvious thing to do, the naive thing to do, the naive/obvious thing is exactly what we did with the sine function. Take the product over all n. So some of these are going to be 0. There's going to be some of these that are 0, and that just, you put a z to the multiplicity. And then let's put 1 minus z over an. Right? Can this be our function f? It vanishes exactly at the an's and at 0 if you like, with whatever multiplicity you like. Does that make sense? What's the problem? Why aren't we done?
Sorry, wait, why do we have the zm at the front?
Terms of this form don't work if the an itself is 0. The function might vanish at the origin. And if it does, I can't use terms that look like 1 minus z over 0.
Okay, so you're just saying if 0 appears in the sequence.
With multiplicity m, yes, including the possibility that m equals 0. There might not be any zeros at 0, in which case m is 0. So this is just number of an's equals 0, which might be 0. Kayla, you had a question? No. Hannah, that's okay? So why aren't we done?
Convergence.
No convergence. We assume nothing about the an's. We assumed absolutely nothing about the an's. We can't get convergence out of this. The an's are completely arbitrary. All we know about them is they go to infinity. Okay? But no convergence. An's go to infinity however slowly they like. However slowly they like. So there's no way to get some convergence on this sum, naively. Here's what Weierstrass does. This is very clever. So Weierstrass fixes it in the following way. So these are called the Weierstrass canonical factors. Canonical factors. If you see this language now, you know what that means. I'm going to set E0 of z to be 1 minus z. And I'm going to set EK of z for k bigger than k at least 1 to be the following: e to the z plus z squared over 2 plus z cubed over 3 plus z to the k over k. Sorry, times 1 minus z. I want that 1 minus z there. Why is he doing this?
It's like the first k terms of the log expansion.
Yes,
right? Yeah.
exactly. This, if I were to extend this, this is the first k terms of log. Log of what? Log of 1 minus z. In fact, negative log of 1 minus z. So if I were to extend this and exponentiate, and e, so 1 minus z times e to the minus log of 1 minus z, that would be 1. So these factors are forcing convergence onto things that don't have convergence a priori. So let me make that very rigorous. Let's prove a lemma. If z in absolute value is less than a half, then ek of z is less than I don't know what it is. I don't remember what it is. I do remember what it is, but let's work it out, and then we'll see if I'm right. Is less than something. Okay, I know what it is. It's some constant. It's some absolute constant independent of k or z times z to the k plus 1. That's what it has to be. And let's see why that's the case. Well, it's exactly what we just did, except more rigorous. So log, so proof, how shall I do this? Let's do it like this. So if z is less than a half, on this disk of z is less than a half, this 1 minus z does not vanish, and so it has a log. So there exists a log of 1 minus z, and such that 1 minus z is equal to e to the log of 1 minus z. And so let's put that in. So ek of z, it's equal to 1 minus z times e to the all this stuff, which we'll write as e to the log of 1 minus z plus, now I'll put in what the stuff was, z plus z squared over 2 plus z cubed over 3, and so on, z to the k over k. Okay? Virgin, you can see that? So this is off by a minus sign, right? The series for here is minus, so let's look at this. Log of 1 minus z plus z up to z to the k over k is negative. We've killed off these first terms, and the next term is negative z to the k plus 1 over k plus 1 minus z to the k plus 2 over k plus 2 minus, and so on. Okay, and now we're going to do just two things. One is to take the absolute value of this difference. What is the absolute value here? Well, z in absolute value is at most a half. So this thing is certainly what? Forget about the denominators. We basically did something very similar. Term by term, this is like 1 over 2 to the k plus 1 over 2 to the k plus 2, and so on. So this is at most, just crudely, it's at most 1. That's one estimate. We're going to do two estimates. So one estimate is that this is at most 1. Another estimate, slightly less crudely, is that we can pull out a factor of z to the k plus 1. And then we're left with 1 over k plus 1 plus, and now let's do things that 1 over 2 to the k plus 2 plus 1 over 2 to the k plus 3, and so on. This is for k at least 1. So we're not looking at the k equals 0 term. Although it's also true for the k equals 0 term, just trivially. So k is at least 1, so k plus 1 is at least a half. And this thing is, so this is a half plus, a half plus a quarter. So this we can take to be 1. Doesn't matter, take this to be 10. This is less than 10. Well, let's be slightly less crude. This is less than 2 z to the k plus 1. Okay? So let's call this whole big thing, let's call this W. So W, what we just learned is that W is less than 1. And in general, if W is less than 1, then e to the W, I want to subtract 1. It's not that ek is this small, it's that it's very close to 1. Yikes. It's not that it's individually small. That's not good. We want it to individually be close to 1. So ek minus 1 is less than this. Sorry, that's my claim. Okay? So e to the W is this minus 1. I'll leave this as an easy exercise. If W is at most 1, then e to the W minus 1 is at most 5W. Just think about the Taylor expansion of E. You subtracted 1, the next term is W, and then there's some limiting thing which is like at most E, but E is less than 5. And the other bound that we have for W is that W is at most 2 norm Z to the k plus 1. So the first bound is here, the second bound is here, and that's what we wanted to show. Any questions? And now we're almost done. Now we're almost done. So I'm going to rewrite this bound just so we can see it. So Weierstrass canonical factors say that ek of z minus 1, I'll get it right this time, is at most 10 z to the k plus 1. This is if z is at most a half. That's what we just proved. So what does he do? So there's some number of zeros at the origin, nothing we can do about that. And then a product over all n. He does a diagonalization argument. And remember what the factors are. ek of z is 1 minus z times e to something. E to the z plus and so on, z to the k over k. Doesn't really matter what this is anymore, now that we've proved this little lemma. My claim is that this function will work.
Do you need 1 minus z over an or something like that?
There is a 1 minus z built into the definition. Does that make
It's
sense?
not en times that, it's en of that. Okay, I see.
En of that. The 1 minus z is built into the definition. So this is really 1 minus z over an times e to the z over an plus yada yada. And so my claim is that this f converges, and hence has only the zeros that it should. Has exactly the zeros that it should. Exactly the zeros it should. Okay, let's see why that's the case. So I'm going to do this ball by ball. So fix some r and let z be in the ball of radius r about the origin. So there are finitely many. There are finitely many, so here's my ball of radius r, z is in here, r. There are finitely many an. The an's are wherever they are. These are the an's. They have to go out to infinity. There are finitely many an that are less than 2r. So I look at this ball of radius 2r, and I'm going to do nothing about those factors. Okay? Then f starts out as z to the m, and then a product over those n's for which an is less than 2r, en of z over an. That's just a finite product. And then there's the product that we're worried about, those n's for which an is greater than 2r, en z of a over n. So it's like a diagonalization argument. I think I said that already. This is like, I guess it's up here. This is like diagonalization. Diagonalization. I get more and more cancellation for every term. You'll see why I'm making a big stink about this. Okay, why am I making this distinction? What do we know about this z over an?
It's less than 1.
It's less than, I gave myself a little more room.
Oh, it's less than 1/2.
It's less than 1/2, exactly. In this range, this z over an, I exactly gave myself the room that I needed. So these are my functions en, and what do I know about en on z over an less than 1/2? The bound that I have is that en z over an minus 1 is an absolute value less than what? Here's my bound, 10 z to the k plus 1. So this is z over an to the n plus 1. But z over an is at most 1/2. 10 times 1 over 2 to the n plus 1. And this is summable. And if 1 minus a function is summable, then the product converges. And if the product converges, it vanishes if and only if one of the terms vanishes. And we're done. That implies this product converges, and since it converges, it vanishes if and only if one term vanishes. In other words, it vanishes at the zeros. One term vanishes. This is true for any r. This is true for any r. Hence, f is entire and has the right zeros.
So why is the argument like diagonalization? I didn't quite
Well,
follow.
I think of it as diagonalization because for every n, I don't know. Whoops. For every n, I don't know how much more concentration I need. It's only diagonalization when compared to the Hadamard theorem, which is what we're going to do next, where the en's, you can have the same n. Instead of having a worse and worse n for every factor, you can have the same n, but that requires the next notion that we're going to look at is functions of finite order. So this is what we're going to do right now after the break. So I will explain why it's diagonalization. I realize maybe I haven't given you all that much intuition for it, or you can just ignore me and have your own interpretation of what it is. It's just words or something. But let's take a couple minutes break and we come back to Hadamard. Okay, so Srirum's remark then can get any poles, any zeros and poles you want. Take the ratio, take a ratio. Okay. So in order to get a refinement of this, where we don't need more and more, where we don't have this diagonalization that I'm referring to, we need a little bit more structure on the function. We need to know something about functions of finite order. Functions of finite, another word that is horribly abused, the order. Yeah, great word, guys. That doesn't mean anything else anywhere else in mathematics. The order of a function. So definition, f is entire, and absolute value of f of z is bounded by e to some constant. There's constants everywhere. Z to some power. So if f is entire and it's bounded by, and there exists c and there exists a k, so that for all z we have something like this, then f has order less than or equal to k. And then if you look at, I guess I should call this k sub f is the infimum over all k such that f has order k. Okay, so the smallest such is the order. Maybe I should call this f has order at most. Okay, I wrote it. F has order at most k, and this is the order of f. Okay, so the least such upper bound. So let's get some examples to see what's going on. Sine of z, order.
Order 1?
Order 1. Order 1, because sine is nothing but the exponential function. It's e to the iz minus e to the minus iz over 2i. Well, in certain directions, this will grow like e to the z, and it's certainly bounded by e to the z, and the exponent of this is 1. Great. E to the z squared has order. There's a nice entire holomorphic function. The order is 2. Thank you, Kayla. E to the z has order. Nice entire holomorphic function.
Infinite?
Infinity. Okay, so this is not a function of finite order. This is a function of infinite order. This is a function of infinite order. This is our enemy from the point of view of understanding things about zeros. Okay, so we want to know about things of finite order. Let me give you one more. Let's see if someone can figure out this one. This is a good one. N goes from 0 to infinity. -1 to the n, z to the n over 2n factorial. If I had a z to the 2n over 2n factorial, what would this be?
Cosine?
Cosine. But I don't have a 2n. I have an n. So it's like cosine of root z. And you can make that rigorous by making a choice of square root and writing out what cosine is in terms of exponentials. And then here you would get square root to the 2n, and square root to the 2n is just z to the n. after some choice. So this you have to worry about. This you don't have to worry about. It's convergent entire. This is clearly entire. It's a convergent power series, convergent on any radius. So what do you think is the order?
1.
1 is a good guess. 1 is a very good guess. It's certainly order at most 1 because it's dominated by the exponential function. But this should smell like e to the I. Kayla?
Is it 1/2?
It's 1/2. Awesome. It's order 1/2. Okay, so order isn't necessarily something that you can easily smell or read off. It's something you have to work a little bit on. But really all we care about is finite, the finiteness of the order most of the time.
Can I ask if we had instead e to the iz, would it be finite order?
E to the IZ, e
No.
to the IZ,
E to the iz. If you put an I.
to the e to the IZ doesn't help because z can also be negative IY.
I see. Okay.
Yep, great question. So it's about the entire behavior of z in any direction. Okay, maybe I'll make that remark. How about e to the iz still has order that is infinite? Okay, so here's a funny fact. Let me motivate Jensen's formula with this fact. I'm going slightly out of order from what I wanted to say, but it's an important comment to make. Okay, so let me state the theorem. The theorem that we're building up to. The theorem is the following: let f have order at most k, and zeros some multiplicity of 0, possibly empty, and then the non-zero zeros. So these are the non-zero zeros. Okay, it can vanish at the origin however many times you want, and then the non-zero zeros. If it has finite order, then two things. If we look at the number of zeros, NR is the number of the zeros, the AJ, including 0, in a ball of radius R. How many of them are there in a ball of radius R? So here's R, and here are my zeros, AJ, and of course they're going out to infinity, and there's some number at the origin. Then this number grows no faster than some constant times r to the k. So the order governs how many zeros there can be in a region. And the second thing is that if you sum the reciprocals of the zeros to the power s, and of course this is why I want to remove, I don't want to take reciprocals of zeros. So that's why I want the non-zero zeros. So these are not in here. This will converge for all s greater than k. These are the two things I want to prove for you. Okay, so this is the main theorem, but I need some lemmata before we get to this theorem. So the point of this theorem is that the order, the growth rate of the function, the e to the z to the k growth rate, that k determines the growth rate of the zeros. The zeros can't grow faster than this, and it determines regions of convergence of, some people call this the Poincare series of the zeros. Some series of the zeros. Okay, so before we can prove that, let's do, we need a formula. Some ingredients in the proof. Ingredients in the proof, which are of independent interest. So this is called Jensen's formula. Some people say Jensen, but I think it's Jensen's formula. Is the following. Let f be holomorphic on some region which contains a disk of radius r about the origin and its closure, just to give me a little room. Then if I integrate, I'm going to write it in a funny way. I don't think this will get me in trouble. I'm going to write it in a funny way. If I take this integral log of f r e to the I theta d theta. So this, if you remember when we were looking at harmonic means, this was before we did the Fourier analysis section. This was like baby Fourier analysis. We saw that functions were, if you have a harmonic function, then its integral average will recover the central value. So the central value would be log of f of 0. But this function has poles. Oh, and is holomorphic and has zeros a1 through a capital N in the disk. In the disk and not on the boundary of the disk. Okay, so there's no problem integrating this on the boundary. On the boundary, it doesn't vanish. This is absolute value, so this is the real logarithm function. So then I have this term minus sum as j goes from 1 to n of log of the absolute values of the aj over r. That is what I claim. That's Jensen's formula. So this is how much we're off by. If f had no zeros, then log would be a nice, well, why would log be a nice function if f had no zeros? Log of absolute value. Okay, I'm getting a little ahead of myself. Let's, you'll see in a second. So let's prove this. So again, here's our disk. Here are our points A, J, and of course I assume that none of the zeros are none of these are equal to 0 because I want to take log of f of 0. So I have these zeros. It's not 0 at the origin, and it's integrable here, and it's holomorphic on a slightly bigger region, omega. So this is r. And so f, if you remember locally, f can be written as z minus a1 times something that doesn't vanish at a1. So we can do that over all of the ai. So z minus an. Let me put it this way. If you look at, let me put it this way. Let g of z be f of z over z minus a1 through z minus an. There's only finitely many zeros here, so we're not worried about any kind of convergence issues. This function has no zeros. Has no zeros. I've removed all the zeros from f. Has no zeros in the disk of radius r, and has removable singularities, and has removable singularities. So if we move them, singularities. So is holomorphic. So f can be written, f of z is equal to z minus a1 through z minus an times g of z, and this does not vanish in the disk. And the nice thing about this problem, the problem of integrating log f, so log of absolute value of f, therefore log of absolute value of f, well, we're taking absolute value, so this is the real log. We're not doing some complex log shenanigans. This is the usual real log. Absolute values of all of these things, that's just the sum, log of z minus a1 plus log of z minus an plus log of absolute value of g. And so this formula is true piece by piece. We will prove we'll prove, let's call this star piece by piece. Okay, so let's look at this part. Let's look at log of g of z. What do I know about 1 over 2 pi integral 0 to 2 pi log of g of z dz? So g doesn't vanish. G is not 0. So there exists a holomorphic function, a holomorphic h, which is log g. And e to the h is g.
Is that supposed to be along the boundary of the circle? Like,
This g is not 0 everywhere inside the circle. G is not 0 on the entire disk and its boundary. G is not 0 anywhere inside.
yeah, but I'm asking about the integral. Like,
Oh, thank you. Yikes. Thank you very much. Of course, I mean r e to the I theta d theta. Yes, I'm integrating along the boundary. Thank you very much, Hannah. Okay, so g is e to the h. What is the absolute value of g?
e to the real part of h?
Yes, awesome. Right? There's a real part and there's an imaginary part, but the imaginary part has absolute value 1. E to the imaginary has absolute value 1, so it's just the real part. In other words, log of absolute value of g is the real part of a holomorphic function. And what do we know about real parts of holomorphic functions? They are
Harmonic.
harmonic. And for harmonic functions, we have the mean value property. And hence we have the mean value property, that this comes out exactly to log of g of 0. Okay. So that captures this formula on the level of at least this contribution. By the way, what is log of f of 0? So we have this formula for a single term, or if you like, if f had no zeros, then this formula would be correct because this sum would be empty. Now let's look at so that was this piece. Now let's look at log of z. So z again will be r e to the I theta minus a1, let's say, doesn't matter which one we take. Now this is an explicit integral. So what will we get? What will we get? So on one hand, let's pull out an r. So this big R can come out because it's log of R plus this thing. So this is equal to log of R plus 1 over 2 pi integral from 0 to 2 pi log absolute value e to the I theta minus, let's call this alpha. Alpha is a1 over r. And all I need to know about this is that it's less than 1. Right? A1 is inside a disk of radius r. So A1 over r is less than 1. D theta. Birchin, I lost you.
Is there 1 over 2 pi in front of log r?
This is a constant, and I integrate from 0 to 2 pi, and then I divide by 1 over 2 pi. Great, thank you. Yeah, so it's an averaging operator, which is why constants come out. Great. Mike, is it hard to see if I zoom in? Is that, I think I zoomed out at some point.
No, it is readable.
Okay. Okay, let me multiply, I'll make a couple more minor modifications. Let me multiply this by a number of absolute value 1, namely e to the minus I theta. This has absolute value 1, so I can write this whole thing as log of 1 minus e to the minus I theta times alpha. And I don't like the minus there, so I'll make a change of variables. Theta goes to minus theta. And hopefully you will see, so let me leave the log r alone. There's a 1 over 2 pi. When I change theta to minus theta, this becomes minus 2 pi to 0. And this has a minus sign, and I can use this minus sign to bring this back to 0 to 2 pi by invariance, by the shift invariance. And then I have log of 1 minus e to the I theta alpha d theta. Okay, so far so good. But look at the function. I'm running out of letters for functions. I'll call it phi. Phi of z defined by 1 minus z alpha. Alpha has absolute value less than 1. This has no zeros, I mean, it's first 0 in the disk of radius 1, because the 0 is at z is equal to, what is it, 1 over alpha, and 1 over alpha has absolute value bigger than 1. Okay, so this function has no zeros. So it has no zeros, so there exists a log. There exists a subfunction psi, which is log phi on this in the disk of radius 1 and a little bit around it. And therefore log of absolute value phi is the real part of psi, same as before. And so this integral is equal to the value. So this is harmonic because it's the real part of a holomorphic function. I'm just running the same argument again. So this is harmonic, and the average value of a harmonic. So this was log of absolute value phi. I hope you see that this is what we're integrating over is exactly the disk of radius 1 of this function of log of phi in absolute value. And so this thing takes on the value at the origin. So this is log of phi of 0, but phi of 0 is 1. So this is log of 1, which is 0. Okay, so again, let's put all of this together. So we did the pieces from here. So if I integrate from 0 to 2 pi, 1 over 2 pi, log of absolute value of f of r e to the I theta d theta, I'll get the integrals over all of these. And the integrals over all of these, let's see. So each of these terms, that's what we did here, that contributes log r plus nothing. So that just contributes log r. Log r plus log r plus log r plus log r. Okay, so we have n of these factors log r. So far, so good. The log of g term contributes log of g0 plus log of g0. Okay. What is log of f at 0? Let me have a little aside here while I still can. What is log of f at 0? So I'm sticking in z equals 0 at all of these things. This is log of absolute value of a1, log of absolute value of a1, plus log of absolute value of an, plus log of absolute value g of 0. You buy that? And so if I take this formula and I add log f of 0 and I subtract log f of 0, and I replace this log of f of 0 by this formula, I think it will be pretty, okay, so then we're almost done. This is log f of 0. This is just the more convenient way to express this thing. I have a plus log g of 0 minus log g of 0, because this is with a minus sign, so g is gone. And then I have the a log of the ai and a log of the r, so that's a minus a sum log of aj over r, as j goes from 1 to n. And that was the claim. That was Jensen's formula. Do you buy that? So if I scroll up a little bit, the claim was that I get log f of 0 minus this sum. And that is indeed what we get. 1 over 2 pi, integral from 0 to 2 pi, log f r e to the I theta d theta is this. Okay, so this is an important formula. This is another one that you might review when you're studying for your qualifying exams. Let's very quickly, we're almost out of time, but I want to get a quick corollary of this, which will make the other theorem go in 5 minutes. Is it okay if I go 5 minutes over? Okay, because I want to be done with this topic and move on to the prime number theorem. But this is an important topic. Okay, so here's a lemma that will be very easy to prove. If we integrate, you remember this n, for some reason there's a delay, n of r was the number of zeros, the number of the zeros, a n, with absolute value at most r. So now I'm again, let's think about just staying in a disk for a minute, and we have some zeros a n, and if we have some smaller radius, little r, then I want to know how many of those zeros are in the smaller radius. So here's a little lemma. The integral from 0 to big R of the number of zeros times dr over r, it's like a logarithmic sum, is in fact equal to a sum as j goes from 1 to big N of this thing, if I had written it properly, which would have been to write it as r over aj. And the aj's are not 0. I don't want any of the zeros at 0. Okay, that's my claim. Why is this true? Let's make a function, the indicator function chi j of r is the indicator function. You see, I start with a very small radius, and at first I don't have any zeros, and then I get larger and larger radius, and then I start catching some zeros. So this is, have we caught up to the jth zero yet? So it's just the indicator function of whether aj is bigger than r or not. And so n of r is just a sum as j goes from 1 to n of chi j of r. This is saying how many zeros have we caught? We're casting a wider and wider net. How many zeros have we caught? Each chi j says, did you catch me yet? So you sum over all of them, that counts how many we've caught. Okay, well, this is completely trivial then, because it's a integral from 0 to r of a sum, and of course I'm going to reverse orders, a sum as j goes from 1 to n of chi j of r dr over r. Does that make sense? All I did is I plugged in what n of r is. But this is 0 or 1. This is 0 or 1. It starts becoming 1 as soon as 1 bigger than aj. So this is actually an integral from aj to r of 1 dr over r, which of course is a log. And the endpoints of the log tell me what they are. Does that make sense? And so we can combine these two formulas by recognizing this as this integral. Let me just write that as a corollary. Corollary, if I take the integral from 0 to r of this nr dr over r, that's this bit. So that's this minus this. So it's the average value of f, of log absolute value of f on this ball, d theta, minus the value at the origin, minus log f of 0. Do you buy that? And so now we can prove this theorem that I wanted to prove at the very beginning, or not the very beginning, this theorem, this main theorem. Remember, I want to prove that the number of zeros grows like this, and that the series converges. So let's prove two things. I'll just rewrite the theorem. So theorem, this is if f has order, finite order at most k, then two things. This function n of r grows at most like some constant r to the k. K doesn't have to be an integer. And if I take the non-zero zeros and I take the series with the power, with exponent s strictly greater than k, then this converges. Those are the two things we want. And now we're very close to a proof. So far, so good? Okay. Here's the idea. The integral from 0 to r, n of r dr. The idea is, the whole idea is do things dyadically, dyadic decomposition. This is, we can't do analysis if we haven't decomposed things dyadically. So everything here is non-negative. So if I drop, if I go from r over 2 to r, I've only decreased the integral. Yes? If eta is an increasing function. So this is at least the value at the boundary. So this is at least the eta of the lower endpoint times, what's this integral of r over 2 to r? It's just some constant, like log 2 or something. Once I pull out that lower bound. Okay, so I pull out the lower bound and then I'm left with a constant. How about here? Now I'm going to apply this lemma. This is just some constant, whatever that is. And this, I'm going to bound by the fact that f has order. So f of r e to the I theta grows at worst, or its log grows at worst like some constant r to the k, right? That's exactly what it means to have order k. So this thing is at most r to the k. So this is a constant times r to the k, and we're done. Are you happy with that? Sriram, something you don't like?
So what was the dyadic decomposition part over here?
It was to think about not the full range 0 to r, but just think about the range r to r over 2.
Okay.
And we're going to do another dyadic decomposition right now. But the proof is okay. Hannah, something you don't like?
So if F has order K,
Yes.
then K is the infimum of
It has
stuff.
order at most K. So it's not the infimum. I'm just doing
Oh,
something
okay,
crudely.
okay, okay.
I'm not getting the exact order. I'm getting some upper bound on the order.
Okay, wouldn't you want to say it's strict there then? Because if it was equal to K, then how do you know that it holds, like that inequality holds if you throw in K?
So all I'm saying is this. That's the assumption that we have order K. It grows at worst like this. So if I take logs, well, you mean plus a constant or something? No, I don't understand.
Well, I'm saying because so the order of F is the infimum of stuff where like that inequality holds, but like how do we know that the inequality still holds for the infimum?
So we don't, and it doesn't have to, and in general it won't. All I'm assuming is that it has order at most K, which just means we have this inequality. I'm not assuming anything
Okay.
about that K is the
Wouldn't we
optimal
want
sum.
to say then like strictly less than K just to avoid an issue like that, or?
The definition of F having order less than or equal to K is that we have a bound like this.
Oh, okay.
So if F has order equal to K, then we don't have a bound like this. We have a bound like this with K plus epsilon for any epsilon. You're absolutely right.
Yeah, so all I'm saying is like take away the equals possibility and write like order strictly less than K. Right?
Oh, I see. You would prefer if I did that. Well,
Yeah.
the definition of this, by definition, this is this. There's two definitions that are being conflated. Even the word order, which is abused, there's the order of a function, which is the infimum, and the function does not actually have order equal to its infimum necessarily. And then there's a function having order at most something. And the definition of having order at most something is literally this inequality.
I don't like that.
I can definitely see your argument. You are absolutely valid in not liking it. Unfortunately, we're sort of stuck with it after the last 150 years of it being in the literature. But I register your dislike and I approve of it.
So just to be
And
clear,
I have to veto it. What's
you're
that, Thomas?
You're saying that a function does not have order, does not necessarily have order at most its order?
Yes.
Okay.
And we will see so the Riemann zeta function grows like e to the z to the 1 plus epsilon for any epsilon. So it has order 1, but it does not grow like e to the absolute value z. I mean, think about e to the z log z is a function. Yeah, okay. Let me, here's a little aside. E to the z log z, in other words, z times e to the z, which is e to the z log z, has order 1, but not order less than or equal to 1. Gosh, Hannah, you're absolutely right. I'm sorry. I wish you were there in 1870 to tell those idiots to get this notation right, but it is what it is. Do you forgive me on behalf of them? Do you forgive them on behalf of me?
I guess it wasn't really up to you, so.
It wasn't up to me. Yeah. You know what? Just for you, we're doing this. Okay, let's make it right.
Thank you.
If you can correct an injustice in history, then why not? All right, let's prove the second thing, and then we're golden. So the second thing, now we're going to do dyadic decomposition. There's a finite sum, finite number of terms, finite number of ANs with absolute value less than 1. So let's separate those out. There's the ANs less than 1, which there's no problem. This is a constant, plus the ANs that are bigger than 1 over AN to the S. Okay, this is bounded by a constant. How about this? Now we're going to do a dyadic decomposition. We're going to catch the ANs depending on what power of 2 oh, I can't use k. What power of 2 they lie between. I guess one of these should be an inequality. Maybe this one's an inequality. So it's the sum as L goes from 0 to infinity. Do you lie between 1 and 2, or between 2 and 4, or between 4 and 8, or between 8 and 16, and so on? Okay, so we're grouping these ANs according to which power of 2 they lie between. And then, so we have this constant in front, a sum as L goes from 0 to infinity. On each of these sums, let's see, an upper bound for this, AN is at least 2 to the L, so an upper bound is 2 to the LS, times how many zeros there are in that interval. And the number of zeros is n of 2 to the L plus 1, crudely. We're overcounting because we're counting in the entire ball and not in the annulus. Okay? But our previous bound says that this grows at most like 2 to the k. So this is a constant, a sum as L goes from 0 to infinity, 1 over 2 to the LS. This thing is at most some constant times 2 to the L plus 1 to the k, which 2 to the k is a fixed constant given to us from the beginning. So this is 2 to the LK, and S is bigger than k, so this is a geometric series that does indeed converge. That's it. That's the argument. It's a very, if you use dyadic decompositions, all of these things, this is a technique of dyadic decomposition. So, okay, what have we done? We've seen that functions of order k have zeros that grow at most polynomially, and the reciprocals of the zeros converge. And since we're already over, I'll take 10 seconds and state Hadamard's theorem, but I won't prove it. Hadamard theorem, which is a bit more involved. If f has order at most k, and let's do it like that, and zeros an, none of whom are 0, then f can be recovered in the following way. F of z is equal to, there's some number of zeros at the origin, there's a product of these Weierstrass factors, but not let L be the floor of k, the nearest integer. So then this will be L z over an. So this is what I mean by diagonalization. This is uniform. You were not taking a better and better Weierstrass factor, canonical factor for each n. This is uniform over n. It's not, doesn't depend on n. And remember, there's an exponential factor. Any two such functions differ by an exponential factor. This exponential factor can be made to be a polynomial. P of z is a polynomial of degree less than or equal to L, where L is the order. Okay, so I'm not going to prove this theorem. I just want you to be aware of it. There's an exact identification for finite order things. If you like, use Weierstrass's theorem, and then you have to get a better and better bound here for every n. That works just fine. Or if you want, you can use Hadamard's theorem, which does this, which gives you some very precise information on the function, which is useful in some applications. But in the interest of time, we will move on. If you forgive me, I have many things to apologize for. But if you forgive me, I will move on to the prime number theorem for the last 3 lectures. And we'll do the Riemann zeta function and the gamma function and all that good stuff. Any questions?